make sure that those who can't attend are able to get this, and we can share it as everyone would like to see it. We have a few folks here with us today. We have Tom Fury, our CEO. He'll be doing the bulk of the presentation here this morning in a couple minutes. We have Matt Hamilton, our CTO, and we have Dave Day, who's our Chief Certification Officer. So we'll be able to provide answers to questions and hopefully a great perspective on what's happening with our technologies and our development. A couple housekeeping things. I'm sure we're all well-versed in Zoomness. If we could make sure we're muted and our cameras are turned off, I think that will give us the best chance for Zoom success here today. Appreciate that. Questions, if you could ask in the chat box as the presentation goes on, I think that would be great. And we'll be able to answer them hopefully all at the end of the presentation or as time allows. And if not, we'll get them answered afterwards without question. So that should work well. Historically, it's worked out pretty well. So another thing, even though this Zoom meeting is scheduled for an hour, we're going to wrap it up in time for any of you or all of you who are going to be attending the next presentation at 9:45 Pacific, which is Overwatch imaging. I'm sure that there's plenty of folks don't want to miss that. So we're going to keep that in mind. And then finally, I'm going to be sending out a note to everybody in attendance afterwards. So you'll have my complete contact information. I've also put my email into the chat. You can grab that. But I'd love to interact with any or all of you individually after this to get understanding of where you are, and if there are questions or things you want to talk through afterwards. I'm really looking forward to that. So without further ado, I'm going to turn you over to Tom Fury again, our CEO, and he will kick things off. Tom, thank you.
Okay. Thank you, Tony, and thank you everyone again for attending this morning, or this evening, this afternoon, depending on your time zone. My name is Tom Fury. As Tony mentioned, I'm the CEO of Sagetec Avionics. And let me share a presentation, and hopefully technology doesn't beat me today, but I think we're okay. Again, CEO of Sagetec Avionics, my email address, tom.fury@sagetec.com, and I welcome you to come to our website, sagetec.com. You can contact us if you have further questions or would like to engage in further discussions. But we're here to talk about UAS situational awareness, and in particular, detect and avoid technologies and as they relate to unmanned aircraft. So first of all, shout out to Howard and the team at Micropilot for putting together this wonderful two-day event for virtual UAV manufacturers meetup. As Tony mentioned, we'll end this prior to 9:45, which is our local time, 45 minutes, so that you can all hop over and join Overwatch Imaging for the next in this amazing two-day event that Howard's put together. And this was one of his posts that he put in LinkedIn the other day about sense and avoid and reliability equals BVLOS. Clearly, there's a lot involved in the ultimate goal of routine beyond visual line of sight flight. One of those things is being able to detect and avoid other airborne objects and other aircraft in particular, and that's kind of what we're here to talk about today. I'll give you a little background on our company at first. Sagetec Avionics is a situational awareness company. We're out of what's called White Salmon, Washington. If you're familiar with the United States, we're in the upper Pacific Northwest on the beautiful Columbia River outside of Portland, Oregon. Our history comes from essentially providing situational awareness solutions to the U.S. Department of Defense, as well as installations in hundreds of unmanned aircraft worldwide with our transponders. Our products have achieved over 1.5 million safe flight hours in military missions. We've sold thousands of units, but we're completely focused on FAA required or certification required situational awareness systems. Our team, Tony mentioned that Dave and Matt are joining us today. Combined, we sit on a lot of regulatory committees for two reasons, both so that we can influence those committees with technologies as they evolve, and or more importantly, so that we can understand the requirements and the technologies that will be required to enable our customers to achieve their goals of flying in national airspace, flying beyond visual line of sight. Those include, if you're familiar with the US FAA structure, the performance standards for subsystems are created by the RTCA Incorporated, and they have subcommittees focused in different areas. So for example, TCAS, or Traffic Alert and Collision Avoidance System, which we'll talk a lot about those systems today in the newest variant called ACAS, Airborne Collision Avoidance Systems. But we also sit on committees around Mode S transponders, ADS-B, Detect and Avoid, ASTM F-38 Committee on Unmanned Aircraft Systems, and then in the US military arena, the AIMS Configuration Control Board. Our technology evolution, so our history comes from developing the world's first micro transponder in around the year 2010. We got that certified by the US military in 2014, and that product has provided situational awareness, and in particular has provided visibility of unmanned aircraft to air traffic controllers and to other aircraft. Since around 2014, when we got that certified, we've been on almost all small or medium-sized unmanned aircraft deployed by the US Department of Defense. We've continued to evolve our technology. Most of the technology we'll talk about today as we implement it is based on the MX platform. The MX platform has achieved certification in February as the world's first NATO DoD IFF, identification friend or foe. So that's a military specific technology. And that was certified by the US Department of Defense AIMS office in February of this year. That platform also has a civil version, which is the MXS, a Mode S ADS-B in and out transponder. We're working on the final stages of certification through the FAA right now with that. But that platform also enables us now to create broader situational awareness solutions, in particular ACAS, or Airborne Collision Avoidance System based DAA, Detect and Avoid systems. And that's kind of what we'll talk about most of today. So it's our belief that DAA systems are a critical technology to helping unleash the phenomenal potential of autonomous unmanned vehicles, as well as advanced electric air vehicles. I've seen reports that say that the eVTOL market, or the advanced electric air vehicle market, will provide $1.5 trillion of economic value in the coming years. And in order to take advantage of that in the eVTOL space and in the unmanned airspace, a critical thing that needs to be accomplished is to be able to enable aircraft to detect and avoid other aircraft, and whether those be other eVTOL aircraft, manned aircraft such as commercial airliners or helicopters, and other unmanned aircraft. All of that is required to take the place of the FAA Part 91 requirement that says a pilot must see and avoid other aircraft. And obviously with autonomous vehicles, the aircraft itself needs to then therefore detect and avoid other aircraft. So what's important is to understand the type of aircraft as well as the space in which you're flying. So there's lots of ways to slice and dice things. A critical way is looking at airspace as it relates to below 400 feet, and these are US requirements, but they're similar worldwide. 120 meters, I think, is the rule in EASA in Europe. And typically between 400 feet and flight level 600, which is approximately 60,000 feet MSL, is the majority of the ATM, or air traffic management controlled airspace. And technologies for situational awareness and detect and avoid in that airspace are going to be technologies based on ACAS, Airborne Collision Avoidance System. We'll talk about that in a minute, but variants called XR and XU. This is for aircraft that are operating under US code Part 91 or Part 135. Below 400 feet, you've got aircraft that are generally operating under Part 107 right now. Part 89 rules apply to them, and I won't get into too much detail about that, but you may be familiar with the remote ID rule that was released just at the end of last year by the FAA, and that requires equipage with remote ID broadcast. Those aircraft flying under Part 91 and Part 135 will typically use ADS-B broadcast. And I'll talk a little bit in a minute about the different technologies that support those. I'm not going to go through this in detail, but what you can see is ACAS, and I'll try and simplify this a little bit, but ACAS is the collision avoidance system that is evolving from TCAS, traffic awareness and collision avoidance system. And TCAS has typically been installed in commercial airliners and business jets. And there are some requirements for flight parameters, such as greater than 100 knots airspeed, typically requiring plus or minus 2,500 feet per minute rate of climb, that made TCAS pretty specific to those types of aircraft. So for example, rotorcraft could not always comply with the collision avoidance commands. Therefore, there was not a rotorcraft centric TCAS solution. ACAS has different variants that attack all different aspects of flight. So what you can see across here is there's ACAS XR, and that's generally for rotorcraft. And there are manned rotorcraft, UAM or AAM vehicles that either will or won't carry a transponder. And that's a 1090 or 978 megahertz transponder, or ADS-B. You've got ACAS SXU, that's for smaller UAS. And I'll talk a minute about how that's defined. You've got ACAS XU, that's for large fixed wing UAS. And then you've got ACAS XA, which is for manned aircraft, and that's similar to TCAS as we know it today. Here's another pretty picture from FAA and NASA, but ACAS X, so this set of solutions is designed for whole airspace protection. You can see I've circled some of the aircraft there. You can see that UTM fits into this as well, with ACAS SXU as a UTM trusted service. And there are specific uniquenesses to each type of aircraft, but in general, ACAS XU is going to apply to fixed wing aircraft that are greater than 55 pounds and that are going to be operating under Part 91 or air traffic control rules. ACAS XR is for manned and unmanned rotorcraft and eVTOL, which obviously is a rotorcraft. They're also going to be in communication with generally in communication with and under control of air traffic control. And then you've got ACAS SXU, and it's not strictly limited to less than 55 pounds or 25 kilograms, but in general, ACAS SXU applies to aircraft that are less than 25 kilograms, but are not flying IFR, so in instrument flight rules, and therefore are not using services of ATC. And that's the big differentiator. ACAS SXU is where air traffic control is not providing, typical air traffic control, ATC is not providing control of the aircraft. ACAS XU, XR, and then the manned versions of XA and XO are under air traffic control. So what is the goal? What is detect and avoid doing? The ultimate goal of detect and avoid solutions are to remain well clear. And there are two types of functions that a DAA system or a detect and avoid system provides. First of all, if you look at the lower graphic, you can see that DAA defines a well clear volume, and that varies based on the aircraft, and it's in the logic that is used in the ACAS logic sets. But a DAA well clear volume provides a safety bubble around an aircraft. And essentially, if there's an intruder aircraft detected, then if there's a potential that that DAA well clear volume bubble will be burst, then the aircraft will receive a remain well clear alert. If it's imminent that a collision might occur, then a collision avoidance command or a resolution advisory will be commanded. The subtle difference between these two is if you're under air traffic control and you get a remain well clear alert, then it's your responsibility to alert the air traffic controller that you've received this alert and coordinate your avoidance maneuver or your remain well clear maneuver with them. If you receive a collision avoidance alert where something is more imminent, then first you follow that collision avoidance alert and then you inform air traffic control that you have just done that and why. So those two different alert functions occur in ACAS XU as well as ACAS XR, plus for manned aircraft, ACAS XA. In ACAS SXU, those two are combined into a single remain well clear, or I should say a single collision avoidance alert. And that is because you're not in communication and you're not under control of air traffic control. So you're not responsible to coordinate your remain well clear with air traffic control. Therefore, you get a single command, and you'll continue to get that command until you avoid the well clear volume of the intruder aircraft. So how does it work? ACAS, again, Airborne Collision Avoidance System, in typical ACAS parlance, and this is XU and XR. So these are under air traffic control type technologies. We classify as two different types of traffic. You've got cooperative traffic, which is essentially another transponder equipped aircraft. They may or may not, typically will have TCAS or another ACAS version. So that's cooperative traffic. But then you've got non-cooperative traffic, who are perfectly legally flying, but do not have a transponder or a collision avoidance system necessarily on board. With ACAS on the right-hand side, you've got ACAS sensors, basically ADS-B receivers, as well as interrogators that both interrogate mode A and C transponders and can validate ADS-B information. Between those two aircraft, you can coordinate maneuvers. So by storing information in registers of the transponders, each aircraft can be aware of the avoidance maneuvers being made by the other aircraft, and you can avoid a situation where, say, two aircraft are in a potential collision course, both choose to climb to avoid that, and they remain now on a collision course. So in typical coordinated maneuvers, one aircraft may climb, the other may descend. On the left-hand side with non-cooperative traffic, you need to have non-cooperative sensors. And for ACAS XU and XR, radar is a required non-cooperative sensor because of its range capability and because of its all-weather capability, but alternate or other additional non-cooperative sensors such as vision systems, EOIR, acoustic sensors, all provide additional non-cooperative target sensing information. You have an onboard DAA computer, and again, many of these components can be combined into a single unit, but basically taking the cooperative traffic information, the non-cooperative traffic information, and providing through what's called a surveillance tracking module, fusing that information together so that you have a single traffic picture of all aircraft. From that, then you have a threat resolution module, which determines if there's a risk of losing well clear, and if so, provides an advisory to remain well clear, as we discussed a minute ago. If there's an imminent risk of loss of well clear, or if there's a loss of well clear, then you get the resolution advisory, which is basically that collision avoidance command that says to take immediate action in order to avoid collision and then inform ATC. So again, this is generally for aircraft using ACAS XU and XR that are under air traffic control, flying in operations under Part 91 or Part 135, for example. ACAS SXU is a little bit different. You've still got cooperative sensors, but these are passive sensors. So you're not transmitting on traditional ADS-B or transponder frequencies of 1090 megahertz or 978, but you are receiving ADS-B information to recognize other aircraft that have transponders. You also have non-cooperative sensors. Now with SXU, all of this can be onboard the aircraft, or parts or all of it even can be offboard the aircraft, and the remain well clear collision avoidance advisories can be provided through the command and control link to the aircraft itself. So again, all or some of these components can be onboard or offboard. You've still got the same situation where you are listening to cooperative sensors as well as using non-cooperative sensors, fusing all of that together in a surveillance tracking module, and then in a threat resolution module, determining whether there's a risk of loss of well clear and providing guidance and taking action. You've also got a vehicle-to-vehicle link now, and this is a separate cooperative communication. It wasn't mentioned in the other chart, but vehicle-to-vehicle links are going to be part of ACAS SXU solutions as well as ACAS XR solutions. So now what traditionally has been called cooperative, non-cooperative traffic is slightly different. If you've got ACAS SXU or ACAS XR, you've got a vehicle-to-vehicle link that helps provide coordination between the two different aircraft. Another difference between this and traditional TCAS is that based on the speeds and the rates of climb that aircraft can now provide, and based on rotorcraft and the vertical velocities they can use and the horizontal velocities they can use, instead of just vertical maneuvering, which is in traditional TCAS solutions, you've got vertical, horizontal, or blended maneuvers for avoidance in ACAS solutions. So we've talked about ACAS, but detect and avoid includes more than just ACAS. And this isn't complete, but in general, what you can see is over on the right-hand side, so in the nose of this notional aircraft, you've got the ACAS system, the DAA computer, you've got non-cooperative traffic sensors as well as the cooperative sensors. So you may have cameras, you will have a radar, etc. You've also got flight control computer, which is a part of the DAA system. You've got your command and control link, whether it's terrestrial or LTE or even SATCOM. That is also considered part of the DAA solution. And then you've got, if there's a pilot in the loop or on the loop, you've got ground station situational awareness displays. All of these are part of the overall DAA solution. So what you'll see in a minute is the subcomponents, each are going to have performance specifications, MOPs, and TSOs awarded to them. But then the overall DAA system, which takes all of that into account, also has system level MOPs and then has a TSO associated with that. But before we get into the specifics about performance standards and TSOs, I'd like to introduce a guest speaker, if you will, Thomas Murray from End State Solutions. And End State Solutions helps companies certify their aircraft. And I think it's important to take a few minutes and talk about the requirements for certifying an aircraft and under the FAA, how that occurs. Thomas? We'll see if we can handle this unmuting thing. Thomas Murray, can you unmute? Tony, can you unmute Thomas? I'll give it another second, and if not, we'll just proceed.
So he should have the ability to unmute himself, I believe.
All right,
Okay.
gentlemen, can you hear?
Oh, there we go.
Can you hear me now?
Yes, sir.
Okay.
I was going to have to dance
So
or
we wanted-
something, so thank you.
Okay, so we wanted to talk about the type design process, because when you have an aircraft and DA components and whatnot, you can't just throw that into the airspace and say we're here to fly. So this is the process used by the FAA. Notice on the right at the very bottom, define requirements, and on the left, find compliance to those requirements that you've defined. And so with the defined requirements, I want you to focus for a moment on the certification basis and the issue papers. And then I wanted to talk about two applied processes as part of this traditional TC process. One is the durability and reliability TC process specific to UAS. Although focused mostly on UAS below 55 pounds, you can work with the FAA to find application for aircraft that are over 55 pounds. The other part is the TSO, and we'll get to that in a moment. Fortunately, in the durability and reliability TC process, the certification basis is already defined in what's called the G1 issue paper. Now, when I used to work at Boeing, it might take us a year to work the certification basis, and then part of that is developing the issue papers. Fortunately, the issue papers have also been defined as well for the durability and reliability TC process. So let's move over into find compliance. So again, with the durability and reliability TC process, that find compliance has already been defined. Unlike when I worked at Boeing, I might have to write reports, analysis, lab testing, demonstrations, flight test, etc. For the durability and reliability TC process, we have a means of compliance that's primarily focused on flight test, and that flight test has 3 particular aspects, and that those aspects, though, are dependent on where the applicant wants to fly. And let's just use 100 people per square mile as the population density over which the applicant would like to fly. In that case, the FAA has again already defined what are the flight test hours. If you don't have a parachute or some other way to decrease the kinetic energy upon impact to the ground, you would have 375 hours. If you do have a parachute or another way to decrease kinetic energy when impacting the ground, it would be 150 flight test hours. And those flight test hours are defined by 3 parts. One is the generic flight testing, simply collecting hours by operational ambient temperature, density, altitude, weights, etc. There are specific testing, though, likely failures, such as what happens when you lose one propulsion unit. Does the airplane remain controlled? And there are also specific demonstrations, but those are a very small portion of what we call the generic flight test hours that are part of this 375 flight test hours. So let's switch for a moment. If we want to talk about component type certificate approval, that's the TSO, or Technical Standard Order, and that's preferred for items like a transponder or the ACAS transmitting processes that Sagetech has. If you don't have a TSO, it likely means you're going to have to write an exemption application, and there's no guarantee you'll get it. It turns out I had to do this in 2015 for one of Sagetech's customers, and fortunately Sagetech's transponder met all the performance requirements, so I was able to get that exemption. However, that exemption is limited generally to 2 years, no more. You can then ask for renewal, but there's no guarantee that you can get that renewal. So that for the applicant, a TSO is always preferred. So that's type design approval in a nutshell. Tom, is that answering what you were hoping for?
Yeah, I'm going to figure out how to permanently unmute myself. But yes, Thomas, I think it does. And I really appreciate that because generally our customers' ultimate goal is to fly without specific waivers, to fly routine beyond visual line of sight. The clearest path to get there for most aircraft is going to be through getting a type certification of that aircraft so that each individual aircraft and operation doesn't need a waiver. And as you've just described, in order to do that, the best situation to get a permanent type certification for an aircraft is to use components in that aircraft that have TSOs, or technical standard orders. Is that a fair summary?
Yes, that is. Thank you, Tom.
Okay, well, thank you, Thomas. Let's so continuing on here on now the specifics of ACAS and the DAA phases that they're going through. Phase 1 has already been completed, and that has enabled unmanned aircraft, large unmanned aircraft, to operate in Class A airspace, which is basically above 18,000 feet, or flight level 180. DAA Phase 2 is almost complete. DAA Phase 2 will enable unmanned aircraft to take off and land in Class C, D, E, and G airspace, to transit Class B airspace, Bravo airspace, and that is your large airports, as well as routine operations in Class D, E, and G airspace. And there are lots of things online to show what these airspaces are if you're not familiar with those. The MOPS have now been completed for this Phase 2, and we're awaiting the FAA to provide the DAA TSO, which we expect in the middle of this year, around July of this year, for that Phase 2. The final phase will be Phase 3 for special cases, and that will occur gradually over the next few years. And that's for HAPS aircraft, high altitude pseudo satellite, I think is the acronym there, small UAS, and that's an ACAS SXU based DAA systems, UAM, AAM, and other eVTOL aircraft, that's ACAS XR, And ACAS XR, again, also includes manned helicopters and Part 135 cargo aircraft. So another eye chart here, but the thing I want to point out with this, I don't want to go through each of the details, but if you look down the left, you'll see, as we described graphically a few pages ago, that DAA systems are more than just ACAS, but ACAS is a fundamental part of that. But there are also performance specifications, MOPS, and TSOs that are or will be associated with ground-based surveillance systems, EO and IR or vision systems. There are MOPS for the ATAR, the second one from the top, which is the air-to-air radar system. There are MOPS for ATCRABs, which is Mode A and C, or Mode S transponders. There are MOPS for ADS-B. There will be MOPS for the 978 alternate UAT frequency ADS-B, as well as terrestrial command and control, including SATCOM, LTE networks. And as you can see, there will be specific MOPS for ACAS SXU and ACAS XR, and guidance material for lost link behaviors and navigation systems. So we won't go through the details of this, but some of the dates to be aware of right now is that the FAA, as I mentioned, or the RTCA just approved the Rev-B MOPS, which is the Phase 2 DAA MOPS for detect and avoid solutions based on ACAS XU. The ACAS XU MOPS that those rely on were approved in December of 2020. And the TSO for both of those is expected this spring and this summer. And then looking to the lower right, for SXU, so for in general, aircraft not under air traffic control and under 55 pounds and below 400 feet operations, those are expected in the middle of next year. So those MOPS are being created as we speak. The initial review of those will start occurring in the fall of this year, September of 2021, and they anticipate approving those MOPS in June of next year. And we are working alongside these different committees so that we're implementing these technologies as the MOPS are written, so that hopefully soon after these MOPS are approved and the TSOs are defined, then we will be able to provide TSO'd systems compatible with ACAS SXU as well as ACAS XR, which is expected in September of 2024. So the challenges, as we get ready to wrap this up, the challenges that unmanned aircraft systems face, obviously size, weight, power, and cost. All of these things, you know, a Phase 1 DAA system could weigh 50 or 60 pounds and cost a lot of money. Putting that on a small aircraft obviously isn't viable. So continued reductions in swap, size, weight, and power, as well as cost of systems, and the trade-off versus performance. So for example, ACAS XU requires onboard radar systems. Those radars are continuing to come down in size, weight, power, and cost, and there's still a big part of the system that presents a challenge for some aircraft. Based on all of these systems, unmanned aircraft need to coordinate with other UTM and ATM aircraft. And on the big eye chart that I presented earlier, one thing you can see is in some cases there's subordinate coordination and junior coordination. Unmanned aircraft essentially need to avoid manned aircraft. So that's a key part of the logic into ACAS systems. And finally, as Thomas just pointed out, a good reason why, systems need to be certified so that aircraft can be certified, so we can get to fully autonomous and routine flight beyond line of sight. ACAS is available today, and we're working with many customers right now on integrating component level solutions into their aircraft. But our ultimate goal is our continued evolution of shrinking those DAA solutions. So this includes for XU and XR, it includes the cooperative surveillance system, as well as the surveillance tracking module, the threat resolution module, all the ACAS computing, all in a single box the size of a deck of cards. And we expect to see those coming out and certifying soon. And those will be compatible with multiple sources of onboard or offboard non-cooperative traffic sensors, such as camera systems and air-to-air radars and acoustic systems. So overall, that's what we continue to expect from DAA. As these rules are emerging, we'll see greater integration of components so that they work together in a certifiable way. And I'm delighted to be that we're continuing to be part of the ecosystem with leading equipment manufacturers such as Micropilot, so that we can work together to ensure that customers have completely certifiable solutions that they can put into their aircraft. We'll see more plug and play sensor options as swap reduces in radars and acoustic and EO/IR systems. Overall, continued reduction in swap in the systems. So with that, I'd like to thank you for joining and for listening. If there are questions, please enter them in the Zoom chat, or Tony can unmute for any questions that are coming in from people on the fly. My email is on there. We will be continuing to communicate people who have expressed interest in this webinar to both provide this webinar as well as to coordinate if further discussions are useful in detect and avoid and situational awareness solutions. Tony?
Yeah, thanks, Tom, very much. That's exactly right. So I'm going to get these slides out to everybody. Had some folks request it. So in my note to all the participants, whether they could make it or not today, those who signed up, we'll get this presentation out, and then we can have further talks if the recording is something you'd like to use to present internally, or to your customers or other folks, whatever that looks like. So this has been a lot of data, I know. And so that'll give also time for some digestion and some, evolving questions that you may have. But like Tom said, we're very ready and able and looking forward to having individual meetings or discussions with any or all of you. And we're getting a little short on time here, so I think we'll go ahead and wrap it up so that you could, again, make that next presentation by Overwatch Imaging, Greg and company. It's going to be a really great presentation. So thank you all very, very much. Thank you, Tom. Here's just a quick question that just came in. What type of radar do you use in the DAA system? Tom, maybe you can take that real quick.
Sure. Well, there are MOPs that define what those radars performance levels they need to be. What we see on the market right now, and I'm not pitching any specific company, but we see customers typically using small radar systems that are similar to counter UAS radars. And there are companies like Echodyne, Fordham, Honeywell are providing these air-to-air radars. What we're seeing is they're right now the size of a paperback book, weigh maybe 2 pounds each. And if you put 1 or 2 of them on there, you'll generally cover your air-to-air requirements. And that'll provide you with visibility of a Cessna-size aircraft, maybe out to about 3 kilometers. But as I mentioned, what we're seeing is that those companies that focus on radars are continuing to expand the capability of it in terms of range and resolution, as well as decreasing the size, weight, power, and hopefully the cost.
One other question that just came in is something, if we could provide some definition about the vehicle-to-vehicle link. And I think that that's still evolving, but Tom, maybe you could touch on that.
Yeah, the vehicle-to-vehicle link protocol is being defined, but then the technology, for example, what frequency it's on, is still not very clearly defined. But essentially, the vehicle-to-vehicle link is going to be very similar to an ADS-B communication protocol, but it's going to be on a different, and I believe controlled, but definitely be on defined frequencies. I really can't give you much more than that because it's one of the last evolving specifications that we see.
Okay, and then real quick again, we'll just keep going with a couple more minutes here, I suppose. From George, how do the V2V solutions circumvent the quote passive sensors only in the SXU class?
I'm not sure what you mean circumvent, but essentially let's jump back to the XU definition. If you remember that, I'll put the slide up here, right? Because this, I think, helps better describe it. So XU, if you remember, the coordination between aircraft occurs through different registers and information provided on transponder frequencies. But aircraft with SXU are not transmitting on those frequencies. The V2V link basically provides a coordination path of that same type of information on a different frequency. So it's not really circumventing, it's working in conjunction with it. So the passive sensors receive ADS-B information from aircraft that are transponder equipped. If those aircraft are V2V link equipped, then the coordination will occur on that frequency.
Okay. And we got one more here. I'll just throw it out here. With regards to the DAA well clear volume, is that volume size defined in a MOP/regulatory manner or more fine-grained with regards to ACAS variant type, in use, airspace, local ATC, other?
It is defined within the well clear volume based on the type of aircraft is defined within the specifications and particularly within the ACAS algorithms. And those are being developed and are developed or are being developed by MIT Lincoln Labs and Johns Hopkins University as part of the TCAS program office of FAA. And for example, the typical well clear volume for a TCAS equipped aircraft or for a manned aircraft is 4,000 foot horizontal missed distance. So that's a radius. And then plus or minus 450 feet vertical. I believe it goes down as low as 50 feet of horizontal missed distance and plus or minus 15 feet vertical for small aircraft, but those are defined directly into the ACAS algorithms based on the type of aircraft that is the intruder aircraft.
Okay. Great. Well, thanks again, everybody. We're up against the next presentation. So again, we'll get this out to everyone and entertain any other questions as time goes on here. I hope everybody has a great week. Tom, thanks very much. That was terrific. I appreciate it. Thanks for everybody for coming. And we hope to see you soon.
Thank you, everyone. We'll see you on the other calls. And Howard, thank you again if you're still on.
Take care, everybody.